Related rates. Let's consider the following example. A ladder 10 feet long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 4 feet per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So here we have a diagram of the situation. Here is the ladder leaning against the wall and standing on the floor. The variable x measures the distance the bottom of the ladder is from the wall, and the variable y measures the distance that the top of the ladder is from the floor. And the length of the ladder is 10 feet. As the ladder slides away from the wall, the top of the ladder will slide down the wall. And it's important to understand in this diagram why these two sides of the triangle are labeled as variables and why this side of the triangle is not. And it is precisely because the length of the ladder does not change during the entire problem, but the distance from the wall and the distance from the floor is constantly changing as the ladder begins to slide away from the wall. This type of problem is called a related rates problem because the distance x is changing and the distance y is changing. And they're changing in a way that they are related to each other. And so the rates of change of y and x are related. And this is why it's called related rates. So let's start to come up with a solution. The first thing we need to do is try to write an equation that represents the relationship between the aspects of the problem that we are interested in. So what is the relationship between x, y, and 10? So we know that in a right triangle, the sum of the squares of the legs must be equal to the square of the hypotenuse. And so we know that x squared plus y squared must be equal to 100. But here is the really important part of this problem. It is true that y and x are related to each other, but they are also each related to an invisible variable, time. So we need to know that the distance x is a function of time, and the distance y is also a function of time. So if you allow me just for a minute, I'm going to say x can really be renamed as x of t. So I'm just saying that x is a function of time, and we can call y of t. And using this notation, I can rewrite my equation to be x of t quantity squared plus y of t quantity squared is equal to 100. And then what I'm going to do is instead of taking the derivative of y with respect to x, I'm going to take the derivative of both sides of this equation with respect to this invisible variable time. And so what we get is the derivative with respect to time of the left-hand side of the equation is equal to the derivative with respect to time of the right-hand side of the equation. And this is just now an implicit differentiation problem. So we are just going to apply the rules of derivatives. So on the left-hand side, we know that we can take the derivative with respect to time of x of t squared plus the derivative with respect to time of y of t squared. And on the right-hand side, let's go ahead and compute this derivative. We know the derivative of a constant with respect to any variable is always equal to 0. Now, what is this derivative here? So we have the derivative of some function of time. So this is just the chain rule. The derivative of anything squared says you're going to bring the power down, subtract 1 from the power, and then multiply by the derivative of the inside. So the derivative is going to be 2 times x of t to the first power multiplied by the derivative with respect to t of x of t. And then we do the same thing for the next term. We're going to get 2 times y of t to the first power times the derivative of y of t. And of course, the derivative of x of t with respect to t is simply x prime of t. So we get 2 times x of t times x prime of t plus 2 times y of t, and the derivative of y of t with respect to t is y prime of t, is equal to 0. And then one other thing I can do here is simply divide both sides of this equation by 2, and that will allow us to cancel out the 2's here. And we end up with x of t times x prime of t plus y of t times y prime of t is equal to 0. Now let's go back and look at what they were asking us to find. So it says the bottom of the ladder slides away from the wall at 4 feet per second. So here's the bottom of the ladder. It is sliding in this direction at 4 feet per second. That is how fast x is changing. So we can say x prime of t, or if you want, you can say dx dt is equal to 4 feet per second. And the question is, how fast is the top of the ladder sliding down the wall? So we can see clearly the top of the ladder will be moving in this direction. And so the rate of change of y is y prime of t, or dy dt. And this is what we are trying to solve. So now let's go down below here and let's solve for y prime of t, because again, this is what we are looking for in this problem. So to solve here, I'm going to subtract x of t times x prime of t from both sides. And when we do this, these cancel out here. And we get y of t times y prime of t is equal to negative x of t times x prime of t. And to solve for y prime of t, I'm just going to divide both sides by y of t. That will cancel this out. And let's bring this solution up above here. We have y prime of t is equal to negative x of t times x prime of t divided by y of t. And just for clarity here, I could use different notation here. I could say dy dt is equal to, and then instead of saying negative x of t here, I could just say negative x with the understanding that x is a function of t, times x prime of t would be dx dt, and then divided by y of t would just be y. So you can write your resulting formula for y prime of t either way. I know these look very different, but they are exactly the same thing. Now, to solve the problem, we need to plug in the values of these variables in order to solve for y prime of t. So again, let's remember we know that dx dt is 4 feet per second. Okay, so we know this variable, but we do not know x or y. So let's read the rest of the problem. It says, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So when this distance is 6 feet. Now it's very important you understand that I did not label this 6 feet in the beginning because this side is changing. Anything that is changing, you want to be sure not to label it as a constant. You must label it as a variable if it's changing. So as these are changing, at some point, the bottom of the ladder is going to be 6 feet from the wall. So at some point, this distance will be 6. What I'm going to do is take a snapshot of that and draw a separate diagram for that particular moment. So here is the moment when the bottom of the ladder is 6 feet from the wall. The length of the ladder is still 10 feet. And then we can solve for what y would be at that moment. Because we know that 6 squared plus y squared is equal to 10 squared. And that's 36 plus y squared is 100. Or y squared equals 64. And that means that y is 8 at that moment. So at the moment that the bottom of the ladder is 6 feet from the wall, the top of the ladder will be 8 feet from the floor. So now I can come back to my formulas and I can plug everything in. So we were told that x was 6 feet from the wall. We just figured out that y is 8 feet from the floor. And they told us in the beginning dx dt is 4 feet per second. So if we plug these in, and I'm using this formula here, we have dy dt is equal to negative 6 feet multiplied by 4 feet per second divided by 8 feet. And if you do the math on this, the feet cancel out here, and you have negative 24 feet per second divided by 8. And this, of course, is negative 3 feet per second. And that's the solution to the problem. So if the bottom of the ladder is moving away from the wall at 4 feet per second, that means x is getting bigger, right? Which is why dx dt is positive. At that same time, the top of the ladder is moving down the wall at negative 3 feet per second. And the reason it's negative is not because it's going down, it's because the length of this side y is getting shorter as it moves down the wall. So that is why our final answer was negative. Now I want to make some additional comments about this problem and the notation. So in the beginning, I had said that we can rename x and y as functions of time by calling them x of t and y of t. And I did that to basically show you why we would be taking the derivative with respect to t and how that notation would help you see the chain rule involved. But this notation is a little bit cumbersome and is unnecessary once you understand what you're doing here. So let me take you through this problem again, but using different notation, and we will move just a little bit quicker. So as we mentioned, we know that x squared plus y squared is equal to 100. And now instead of rewriting these as functions of time, let me just have an understanding that both x and y are functions of time. So what I'm going to do is take the derivative with respect to time of the left side, and this will be equal to the derivative with respect to time of the right side. And now the derivative of x squared, of course, we know is 2x, but then we have to remember to use the chain rule and multiply by the derivative of x with respect to time. And then when you take the derivative of y squared, it's the same thing. It's 2y times the derivative of y with respect to time, and the derivative of a constant is equal to 0. And then from here, when you solve for dy dt, you will, of course, get the same answer that we had a few minutes ago. But the point of me showing you this is that the notation is much simpler to not use the function notation here for x and y. So if you don't have to use x of t and y of t to understand what you're doing, it is my opinion that this notation is better. Now, the rest of the problem would be the same. You would plug in x equals 6. You would solve for y, which we found to be 8. And then you would plug in dx dt is 4 feet per second. And then you would get your answer that we got a few minutes ago. Now what I would like to do is ask a related question. Suppose I was interested in the behavior of the angle theta down here. And as the ladder slides away from the wall, the top of the ladder slides down the wall. Therefore, the angle theta would be changing, this angle here, and it would in fact be getting smaller. So I can ask a question like, how fast is the angle that the ladder makes with the floor changing at this instant? And when I say this instant, I'm talking about at the instant that the bottom of the ladder is 6 feet from the wall. So to solve this problem, we would need to have a new equation. X squared plus y squared equals 10 squared does not involve theta. So we would have to use trigonometric functions to bring theta into the problem. Now, I could set this up a number of ways, but the easiest way to set this up would either be to say sine of theta is equal to y divided by 10, or I could say cosine of theta is equal to x divided by 10. Both of those are true from the basic definitions of sine and cosine. But for this particular problem, I think I would prefer to use this one. Now think about why I would prefer to use this one. Why do I prefer cosine of theta equals x over 10? Is it because I prefer cosine over sine? Well, no. It's because I prefer x instead of y. And the reason I prefer x is because the information that they gave us in the problem was about x, right? So let's not forget that dx dt is 4 feet per second. And we want to know what's happening at the moment that x is equal to 6 feet. So all the information they've given me is about x. So you could do it using the other formula, but it's going to be more work. So let's stick with this one. Now what we need to do with this formula is bring in the derivatives, bring in the rates of change. Now one thing that I'm going to do just to help this be a little bit easier is I'm going to multiply both sides by 10, which is going to give me 10 cosine of theta is equal to x. This gets rid of the fraction. And then I'm going to take the derivative of the left side with respect to t, and I'll take the derivative of the right side with respect to t. So let's remember our trigonometric derivatives. So here we have the derivative of a constant times cosine. So the constant 10 will come down. And the derivative of cosine of theta is negative sine of theta. And then we have to multiply by d theta dt. This is the chain rule. On the other side, we have the derivative of x with respect to t, which is dx dt. So if I simplify, on the left side I have negative 10 times the sine of theta times d theta dt is equal to dx dt. And they're asking how fast is the angle the ladder makes with the floor changing. So that is d theta dt. So to get that by itself, I'm going to divide both sides by negative 10 sine of theta. On the left-hand side, these cancel out, and we end up with d theta dt is equal to dx dt divided by negative 10 times the sine of theta. So now we just need to plug in the values. Of course, we know dx dt is 4 feet per second. We know that this 10 right here is really 10 feet because that's the length of the ladder. So we're going to write negative 10 feet. And then we have the sine of theta, and that's the big question. What is the sine of theta equal to at that instant? So remember earlier, we mentioned that if you take the moment when x is 6 and the ladder is 10, you can solve for what y is. And we found out that y was equal to 8. And if this is theta, at that moment, you can say the sine of theta is equal to the opposite side divided by the hypotenuse. So that's 8 divided by 10, which can be simplified to 4/5. So again, by setting up a very simple diagram, we can figure out that sine of theta at this instant is 4/5. And now I'll just come down here and I'll replace sine of theta with 4/5. And now we'll do the math here. So we have 4 feet per second divided by negative 10 times 4 is negative 40, divided by 5 is negative 8, and this will be feet. And this is negative 1/2. And what happens here is the feet cancel out, and you get kind of a strange unit. You get blanks per second because these are gone now. And the blanks are radians. So the answer is d theta dt is equal to negative 1/2 radian per second. That is how fast the angle is changing at that instant. In case you're interested, I will tell you that negative 1/2 radian per second, if you were to think of this in degrees, it is approximately negative 29 degrees per second. So that's how fast the angle is changing at that particular instant. Now, I will say in calculus, we don't do this. We don't give the answers in degrees. We always give our answers in radians. In the next example, if A is the area of the circle with radius r, and the circle expands as time passes, find dA dt in terms of dr dt. So here we have a circle, and the radius of the circle is r. And we should know that the area of a circle is pi times the radius squared. And if I abbreviate the area using the letter A, we can write A equals pi r squared. Now, if the circle is increasing in size, so that means that it is expanding outward in all directions, that would of course mean that the area of the circle is getting larger and the radius is getting larger. So that means that both A and R will increase. So they are both functions of time. So just like in the last example, if I take the derivative with respect to time of the left-hand side of the equation, this is equal to the derivative with respect to time of the right-hand side of the equation. And now the derivative of A, of course, is just dA dt. And on the other side here, let's remember that pi is a constant. So the derivative of pi r squared is pi times the derivative of r squared, which is 2r. And then, of course, the chain rule says dr dt. So if I clean this up here just a little bit, I will write dA dt is equal to 2 pi r times dr dt. And this is the answer to part A, because part A was asking for dA dt in terms of dr dt. So we now have a relationship between those two quantities. For part B, it says, suppose oil spills from a ruptured tanker and spreads in a circular pattern. So like this. If the radius of the oil spill increases at a constant rate of 2 meters per second, how fast is the area of the spill increasing when the radius is 30 meters? So in part B, they tell you that the radius is changing, so that's dr dt, at a constant rate of 2 meters per second. And they also tell you that the radius is 30 meters at some point, and at that point, they want you to tell them how fast the area is increasing. So they are asking you to find dA dt. So of course, to do this, all we have to do is use the formula that we found down here and simply plug in the values of r and dr dt. So dA dt will be equal to 2 pi times the radius, which they tell us is 30 meters, times dr dt, which is 2 meters per second. And if we multiply these numbers together, 2 times 30 is 60. 60 times 2 is 120. So we have 120. And don't forget there's a pi here, so let's write that down. And then we have meters times meters per second. And that is meters squared per second. And this is how fast the area is changing at that particular moment. For the next example, the radius of a sphere is increasing at a rate of 4 millimeters per second. How fast is the volume increasing when the diameter is 80 millimeters? Okay, so in this problem, we are talking about a sphere. A sphere is a fancy word for a perfectly circular ball. And this sphere will have a radius r. Now, to do this problem, we have to know the volume formulas for a sphere. And I will tell you that the volume of a sphere is 4/3 pi r to the third power. And let's abbreviate that by calling the volume V. So V equals 4/3 pi r to the third. Now the question is, how fast is the volume increasing when the diameter is 80 millimeters? And the radius, we already know, is increasing at 4 millimeters per second. So let's write down what we know. dr dt, the rate of change of the radius, is 4 millimeters per second. Now they tell us that there's a moment where the diameter is 80 millimeters. So you need to remember that the diameter is the distance all the way across the sphere. So the diameter is equal to 2 times the radius. So if the diameter is 80, then of course that means that the radius is 40. So this is the information that they give us, but the information that we're going to use is the radius is always half of the diameter. Now the reason we're not using the diameter is because there is no diameter in this formula. There's only radius. So that's why I needed to figure that out. Now let's take the derivative of both sides with respect to time. So I have derivative respect to time of v equals the derivative with respect to time of 4/3 pi r to the third. On the left side, of course, we get dv dt. On the right side, we have a constant 4/3 pi, and then we're going to multiply that by the derivative of r cubed, which is 3r squared times dr dt. And we could do a little bit of simplifying here. The 3's cancel out, and we get dv dt is 4 pi r squared times dr dt. And then, of course, the last step is we just need to take these values and plug them into that equation. So we have 4 pi times r, which is 40 millimeters, squared, times dr dt, which is 4 millimeters per second. And now we just need to complete this. We have 4 pi, 40 squared is 1600, and we're going to have millimeters squared, and then times 4 millimeters per second. And now let's just multiply this together. 4 times 1600 is 6400, and 6400 times 4 is 25,600. And then don't forget you have a pi there. And then millimeters squared times millimeters is millimeters cubed, and then per second. In the next example, we have an inverted circular cone water tank with base radius 2 meters and a height of 4 meters. Water is being pumped into the tank at a rate of 2 cubic meters per minute. Find the rate at which the water level is rising when the water is 3 meters deep. Okay, so an inverted cone is a cone that is upside down. And in this problem, we are talking about the volume of this cone. Because if water is being pumped into it, that's a volume, right? That's a change in the volume. So what is the volume of a cone? The volume is 1/3 pi r squared times h. Now, this is the volume of the water in the cone when it's at this level. So you can see the radius here is r, the height here is h. But I want you to notice that you have similar triangles here. We have a right triangle here, we have a right triangle here, and this right triangle is similar to this right triangle. And we know that this total distance here is 4, and this total distance here is h. And because these triangles are similar, we can set up a proportion by comparing like sides. So I can say r compares to h the same way that 2 compares to 4. And if I cross multiply, I get 4 times r is equal to 2 times h. And from there, if I divide by 2, I can say h is equal to 2r. Or I can say r is equal to h divided by 2. Now, what does this allow us to do? Well, it allows us to get rid of one of these variables. So I can go in two directions here. If I plug 2r into here for h, I'm going to get the volume equals 1/3 pi r squared times 2r. And this will be 1/3 pi r cubed, and then multiplied by 2 will actually change this to 2/3. So this is one possible formula for the volume. But I don't have to make that substitution. I could also say R is equal to H over 2. And I could put H over 2 in for R. And if I do that, the volume becomes 1/3 pi times H over 2 squared times H. And this is 1/3 pi times H squared over 4 times H, which is 1/12 pi H cubed. So for this particular cone, both of these volume formulas are valid. One of them is expressed as volume as a function of R. The other one is expressed as volume as a function of H. Now, we're not going to use both formulas. We're going to pick one. So let's read the problem again here. If the water is being pumped into the tank at a rate of 2 cubic meters per minute, find the rate at which the water level is rising when the water is 3 meters deep. They are giving us information about the depth of the water. That is this variable here. So they are telling us about H. So you can interpret this to say H is 3 meters deep, and you are looking for dH dt, because you want to know how fast is the water level rising. Now we know that water is being pumped into the tank at 2 cubic meters per minute. This is how fast the volume is changing. So this is dV dt. So I hope what you see is that we are going to be using this formula. We need the formula that involves H, since the information they give us is about H and the information they ask for is about H. So we are going to take this formula here and take the derivative of both sides with respect to time. So the derivative of v with respect to t is dv dt. The derivative here, we're going to keep the constant 1/12 pi times the derivative of h cubed is 3h squared times dh dt. And this means that dv dt will be equal to 1/4 pi h squared times dh dt. And all I did here is cancel 3, goes into 12, 4 times. Now, they are asking about dH dt, so we need to solve for dH dt. To do this, I'm going to multiply both sides by 4. This will cancel this, and we get 4 times dV dt is equal to pi h squared times dH dt. And then to solve for dH dt, I will divide both sides by pi h squared. This will cancel out, and we end up with dH dt is 4 times dV dt divided by pi h squared. And now I'm just going to plug in the information that they gave us. So we know the volume is increasing at a rate of 2 cubic meters per minute. And then down below we have pi times h squared, and they tell us that h is 3 meters. And don't forget to square it. And now do the math. 4 times 2 is 8. In the bottom you have 3 squared, which is 9 times pi. And the units are cubic meters divided by square meters, which are just going to be meters, and then per minute. And this is how fast the water level is changing at that instant. So what's important to say here is that there are times when your formulas will involve more than 2 variables. In this case, there were 3 variables, but they will give you some information about the relationship between 2 of those variables, like over here we could figure out that the height is always twice the radius, for example. And that allows us to plug in for one of those variables and simplify your equation. But again, it depends on which equation you're going to use. So you have to figure out which one to use, and then from there you can do a simple derivative of both sides and solve your related rates problem. So I know these things seem kind of challenging, but trust me, with practice, it will get better. And that concludes this video lesson.